So the plan for this divide and conquer chapter is that um, we will start with an example called maximum subarray problem, and we will introduce the solutions to it, and we'll analyze its code, and basically that will lead us to the solution of it in a similar form as solving the recurrence as we did for the merge sort. So, and then we can realize that actually the divide and conquer algorithms, this big family of algorithms, can all kind of be described with a recurrence equation or just recurrences for its running time analysis. So how do we solve the recurrence becomes a core problem or core question that we need to answer so that we can have a more general solutions to these kind of divide and conquer algorithms. Okay, so today I think we will have time to cover the introduction example of maximum subarray, and after the lecture, later this evening, I will release the homework, the programming homework for this chapter for divide and conquer, and we will implement the maximum subarray problem and another variant of it. Okay, and for the paper-based assignment, for the paper-based question set, there will be more questions, but I will also give you a relatively longer time to work on it, and it will be more about how to solve the recurrences and how to analyze the running time on the paper. Okay, so today let's see if we can cover the introduction level, introduction example, and the next week we will stay on the same chapter but introduce the solutions, the general solutions with more details. All right. Okay, so we already have some sense about how divide and conquer algorithm works. So merge sort is a very typical example. So we have three basic steps in order to do this, to carry out to divide and conquer. First, we want to divide the problem into several sub-problems. And those sub-problems, they are the smaller instances of the same type of problem. Okay, only smaller in magnitude. Okay, after we dividing the problem, we have a new type of problem, then it's not applicable by the divide and conquer algorithm. And second step, we solve all the sub-problems recursively. Okay, so recursion is one of the characteristics of divide and conquer algorithms. And the last step, of course, is to collect all the solutions from all these sub-problems. And we want to merge or want to combine the solutions into a solution of the original problem. Okay. So when we have recursions, we need to consider when the conditions of the recursive operations. Okay, so when the sub-problems are larger than the basic case or than the boundary case, we need to use a recursive style, right, to solve it. In merge sort, when we have a input sequence that has more than 2 numbers, then we will call the algorithm, call the merge sort recursively. Okay, but in other case, in the base case, when the problem is just when the input sequence just only have 1 number, then we will basically do nothing, right? So that is the basic case running time. Okay, basic case situation. So when we analyze the divide and conquer solutions to the examples today, we will find that we have very similar paradigms. Okay, we need to divide to get the subproblems, to conquer them recursively, and then combine their solutions. So maximum subarray is the example that we will cover today. And in our next week's plan, we will introduce the general solution, and also we will cover a second type, which is the matrix multiplication problem. Okay. All right. So the term that we will need to, the technique that we will need to use for describing running time is the recurrence. Okay, so it's actually an question on an equation or inequality that describes the function in terms of small inputs, right? For the merge sorts, we describe the function of it with a function t of n, and we will split the function into two cases. The first case is a base case, right, which takes constant time, and for the recursive cases, we describe the running time with the function itself, right? The t of n over 2 is a function itself, but with a smaller inputs, half of the n, because we split the original problem into two halves. Okay, and the theta of n is the costs that comes with the division and the combining step. So for merge sorts, we have defined a merge procedure, right? That takes two already sorted sub-arrays and merge them into one complete array. So that cost running time, the running time of that procedure is basically the big theta of n. So that we need to include that into the recurrence equations. All right, but sometimes we can have different forms other than a regular equation, recurrence like this. Sometimes the division of sub-problems may be unequal sizes. For example, in this particular recurrence, the running time for solving the original problem, which has n as inputs, is actually the summation of the same running time on the first 2/3 of the inputs and the last 1/3. Okay, and the cost for dividing and the combining. Okay, so we are not aware, we don't know what the specific problem is, but it's possible. It's possible that we can divide the problems into unequal sizes, right? Depending on what prior knowledge we know about the inputs, right? And in other more rare cases, we can even have dividings results like this. We basically solve the original problem by solving a smaller problem that is only one element fewer than the original input. That is also possible, okay? But this is different from the two cases above, because now the subproblem is not a constant fraction, and this totally changes the nature of the problem. Okay. And the most common cases for divide and conquer is that we will divide the problem into constant fractions, either half, so half the size of the problem is the most common, or we divide it into constant fractions. All right. Okay, so there are some simplified technicalities in recurrences, because if we think about the merge sort procedure more carefully, we really should use those ceiling and flooring symbols. That is because we don't know whether it's an even number or odd number for the inputs, right? But this is something we can tolerance if we can basically ignore the floor or ceiling or boundary conditions. Okay, so that we will get a general idea, but rather than um, covering all the details. So like the base here, we can remove it. We can just keep the recursive case, and we can basically like use 2 times n/2 without the setting or flooring. Okay, just for a more compact um, narrative of the problem. Okay. So as an overview here, we will introduce several terms. The ultimate goal of this chapter is to introduce a more systematic way to solve the recurrences. Okay, what we have already done with the merge sort is that we draw the recursion trees, right? And we sum up all the nodes in that tree, and the summation, the summation results will be the total, will be the final running time for the algorithm. And we will see that we have a faster way of achieving the same goal once we have known more properties about the recurrences. Okay, we don't really need to draw a complete tree each time we see a recurrences. Okay, so the method that we will introduce in this chapter includes the substitution method. Okay, so this method relies on mathematical induction. Okay, so it's a technique to prove a problem from some guess we have, and from a smaller case to a bigger case, and until all cases approve. All cases are approved. Okay, and the second is what we have used before, is the recurring tree method, right? We draw the tree with all the nodes and try to sum up all the nodes. And the last general solution is called the master theorem. So it provides a generic solutions to all the recurrences, as long as they satisfy these formats. Okay, right. So right now we don't need to understand why this is the case, but we will have a comprehensive introduction about the method, and we will see that it's quite related to how recursion tree method is used. Okay, so as long as we have any recurrences that look like this form, we know the constant a, we know the size of the smaller subproblem, and we know the function associated with combining and dividing, then we can like immediately tell the solutions of the problem. Yes, so T of n is a function to describe the running time of an algorithm. All right. So that is an overall overview of the goal of the chapter. And today we will start with a algorithm which solves the maximum subarray problem. Okay, I think it's also a typical example of divide and conquer, and it's I think it's fun to look at, and I think it does have a pretty broad applications, even in a lot of the real world problems. All right, so as the name indicates, we want to find the maximum subarray within a input array, right? But let's put the problem into a more concrete scenario. So imagine we are considering an investment problem. Okay, we want to either invest in stock markets or whatever markets we're interested in. So the strategy is that we want to like buy one share at one time, and then we want to sell it at a later time. And hopefully we buy it at a low price and sell it at a higher price, right? That is the basic strategies of doing investments. Okay. So for example, if we kind of cheat a little bit by knowing all the prices in advance, okay? We know the price for a stock, like for all these days, like from day 0 to day 16, we know 17 days, all the prices, right? And we can quickly plot all these price. And then our goal is to, we want to find a day to buy and a later day to sell so that our profits is maximized. Okay, so it looks like a pretty common problem and a pretty relevant problem. Okay, so let's think about whether there are some ways we can or whether there are some strategies we can hold on to, we can rely on. So I think one of the most typical thought is that we probably want to find the lowest point to buy and find the highest point to sell. Okay, right? But since we have limits, we have constraints, because once we have found the lowest points in terms of price, then we have to sell at the later date, right? So we have to find the highest price to the right of the lowest price. We cannot sell ahead of buying it, right? And also, when we find the highest price throughout all these days, find the highest points, and when we try to find the lowest price to buy, we have to try to find it towards the left of the highest price. Okay, so you see the point is that the setting point and the buying point, they must be in temporal order, right? All right, so let's look at the example, and what we can do is to find the lowest and the highest price. And then from the highest price, what we can do is to, so let's first look at the lowest point. So because this one is our lowest point, right? So after we find the lowest point, then we should scan the right parts of the curve and try to find the highest price, which is here, right? We should never look at the left part, right? Because we are not allowed to sell it ahead of time, right? So that is our lowest, and that's the highest to the right of the lowest. So this one probably give us a pretty nice price, right? Or we can find the highest price over at all time, right? So this point is the highest point at all time among these 17 days. So after we find the highest point, we should look at the left part of these points and try to find the lowest price, which is this point here. So obviously in this scenario, the green solution is not as good as the red solution, right? But we can always compare, right? We can take these two pairs and try to find the greater, just to keep the one that gives us the greater difference, right? So they tell us that we should buy at day 7 and sell it at day 11. Okay, so it seems like this is a nice strategy, right? It makes sense, and also it's not hard to implement, right? All we need to do is to find the global highest point and lowest point and work on each case respectively, and then compare the final differences, right? All right, but in terms that, it turns out that this is not a right way. Okay, sometimes it does not always work. Okay. So look at this strange curve, maybe. Yeah. So you can see that the overall trend is decreasing, right? The price is decreasing. But there is a segment among this decreasing trend, there's a sharp increase as well from day 2 to day 3. So if we stick with this old strategy, say we find the global highest point and the lowest points, right? And we need to find the lowest, after we find the highest point here, we have to buy it here, right? And after we find the lowest point here, actually there's no way to sell it anymore, right? Because we buy it at the last date. Okay, so it seems that according to the strategy, we have to buy in at these points at day 0 and sell out at day 1, right? But obviously we can tell this is not good as buying in at day 2 and sell out at day 3, right? Because we can, with a glance, we can notice that this is a larger difference. Okay, so we need to think about the problem in a different angle again, because in this scenario, the best buy-in date and sell-out date, they are not the global minimum or maximum price. Okay, so it really doesn't matter if the buying points or the selling point is the global minimum or maximum point. Actually, it is the difference that we care. Okay, it is not the absolute value that we should care more about. All right. So let's break down into the problem more and try to kind of brute force out the problem. So basically, any kind of problems can be brute out, right? If we think about like to basically iterate over all possible solutions. Okay, and obviously in this case we can do that, right? Because we already have the price for each day. All we need to do is to try every possible pair of buy and sell dates, right? So that is a quite straightforward solution that we can get. So these segments, I mean, this pseudocode of implementation is something you can find on the textbook. So what basically it does, right, is to, use a 2-layer of for loop, right? And the outer loop ranges over all possible buy-in dates, right, from low to high -1. And the second layer for loop starts with I + 1. You see, so it must, the sellout date must be to the right of the buying date. So the J needs to start to the right of I, right? And we compute the difference between any pair of I and J, right? And if that profit is greater than the current maximum profits, we will need to mark all those I and J and profits, and then we finally return it, right? So I think that's a quite straightforward solution, because we are using 2 loop counters with the 2-layer nested for loop to scan over the price table, right? So it's a solution that works. That's something we can easily realize, but the running time efficiency is another issue, right? So we have to make sure actually the running time actually results in a quadratic time efficiency. Basically, there are so many in a loop, so many executions of code with the nested 2 for loops, right? It's basically like, you can think of it the problem of picking 2 out of n numbers to calculate how many unique combinations are there. So it's a typical discrete math problem here. Okay, so that is not ideal, right? Because we know that a quadratic running time algorithm can be really inefficient when the input grows really big. Okay, so there's a need for us to think about whether there's a way to further optimize the problem, right? So ideally, we want to introduce something that can like run in a logarithm in a logarithm running time, right? Yeah. So let's in order to achieve the goal, let's have a little transformation of the problem. Okay. So basically, let's rephrase the problem, because the original problem is to find the buy date and the sell dates, right? But we can translate into a new problem, which is to find a sequence of days. Over that sequence, the net change from the first to the last is maximum. Okay, so we want to kind of monitor the net change, right? Which is whether it's increase or decrease. It could be positive or negative, but we want to maximize that net change. Okay, so we can further like define the daily change, which is the current price minus the price of the previous date. Okay, so given the table, we can basically attach an additional row, which is the daily change value, right? So the daily change for 0 is unavailable because that's our first elements. And the daily change for day 1 is 113 minus the previous price, okay? So that's how we get all those daily changes. So, you know, sometimes the daily change can be negative. But now, after we have doing this transformation, the problems can be rephrased with a difference term. Okay, so now we basically want to find a contiguous subarray of A. So notice that the A here is the third row. Okay, it's the table, it's the element, the array of net changes of each day, except the day 0. Rather, A is not the price. Okay, so here A is not the price. We want to find the contiguous subarray of A, and we want to that subarray has the maximum or the largest sum. Okay, so this is where the maximum subarray comes from. Okay, so this contiguous subarray is the maximum subarray. So in this case, it is a subarray that looks like this. Okay, and I think the subarray is not unique. The maximum subarray is not unique. There could be duplicates, but here we will consider the simplest case, right? And in this example, we can see that the maximum subarray ranges from day 8 to day 11, which gives you a total net change of 43 in terms of price. All right, so it's just a transformation. We don't know how to we don't know how to solve it yet. Okay, actually, if we only have this transformation, because it doesn't help yet. Okay, it doesn't help so far, because if we just stick with the brute force method, we still need to check that many quadratic amount of subarrays. Okay, so now we need to consider the efficient solution. We need to consider the divide and conquer approach. Okay. All right, so let's think about the problem. Okay, we want to find the maximum subarray from low to high. Okay, so let's just divide it, okay? And then a straightforward way is to find for any array, right? For any input array, a straightforward way is to find the midpoint so that we can have two sub-arrays, right? First one is from low to mid, second one from mid plus one to high, right? So the next statements or the next claim is important, okay? So when we consider any sub-array from index I to index J of the original array from low to high, right? So I and J, they must be within the range of low and high, okay? So for any sub-array I and J, they must be exactly one of the three cases. The first case, it's entirely in the left sub-array, right? Which means the two indices I and J are greater than or equal to low and bounded by midpoints. Okay, they are entirely in the left sub-array. Or they are entirely in the right sub-array, which is bounded by mid plus one to high. Right, that's two cases. And the third case is that the sub-array crosses the midpoints. Okay, which means that the I can range from low to mid, okay? But the J is greater than mid and bounded by high. That's the three cases that exhaustively cover any cases of sub-array. Okay, so I'll give you a few seconds to think about whether this is the case. Okay, let's see if we can try to figure out any other cases other than these three cases as a sub-array of the original array. Right. Yeah, actually we cannot find.
Wait, couldn't there be no like couldn't it all be negative if it was just falling all the way down? Is that one?
Can you say that again?
Could it just be continuously going down and there is no subarrays? Could that be a case?
There's no sub-array. But we can always find a sub-array once we know where the original array starts and original where the starting index is and the end index is. Right, as long as the original array is defined within a with a limited range, then we can always find any sub-array.
Got it. Thank you.
Yeah, if the I and J exceeds low or high, then it is not a valid sub-array, right? It's no longer a sub-array. So when we talk about sub-array, it must be one of those three cases. Yeah. And so one comment that seems like insider trading. Yeah, I think it's a theoretical problem. Okay, in real life, it doesn't occur. It doesn't happen that we can know the price of the future. It just provides kind of an analytical practices. Yeah, there could be more than one sub-array that has the maximum net change. Yeah, if they yield the same net change. I think that's true. All right. Okay, so let's carry on with the problem. Right. So it's kind of gives us hope, right? Given after we dividing the original input into two halves, then we can have three cases. And all we need to do is to solve these three cases individually. Let's see if we can do that. Okay. So a maximum subarray also must be one of the three, right? Eventually the subarray that has the maximum summation must belong to either one of these three cases. All right, so now it's time to think about the recursive solutions. Okay, we can actually find the maximum subarray for the array from low to mid, which is the left half of the original one, and the right half from mid plus 1 to high recursively, because they are the smaller instances of the original problem. They are the sub-problems, right? So we can just directly recursively call our algorithm on the left half and on the right half, which covers the first two cases, right? But for the third case, the maximum subarray that crosses the midpoint, that is a special case. It is not the smaller instance of the original problem, because it has a constraint, right? It has a constraint. It confines that the starting index and the ending index of the subarray must cross the midpoints, okay? So it's not a free problem, okay? It's a constrained problem, okay? So for that special case, we need to solve it manually. We should not use a recursive call to solve it, okay? And finally, after we have three solutions, basically, right? We have find the maximum subarray from the left half, from the right half, and then from the third case that across the midpoints. We just compare the three items between these three, the three items, and find the one that has the largest summation, right? So in theory, that should give us the solution to the problem. All right, so we can basically consider these three steps as the conquering steps, right? And after we compare the three summations, we find a larger one, which is the combined step. All right, so on next page here, I have a visualized process of what's described in the previous slide. Okay, so given an input array, we want to find the midpoints to split into two halves. So any subarrays can either be entirely within the first half or entirely within the second half or cross the midpoints. Okay. So in this case, if a subarray that crosses the midpoints, there are actually two parts of it, right? We are considering the third case. We're considering the case where the subarray crosses midpoints. So in this case, the starting index I should be between low and mid, okay? And by our definition here, it can actually reaches mid, okay? But it should never cross mid. And the ending index J must be greater than mid. So it starts with mid plus 1 and can be bounded by the high index. Okay. So basically, the divide and conquer approach needs to find the maximum subarrays that has the largest summation among three cases, right? The first case corresponds to the left subproblem. The second, the green one, corresponds to the right subproblem. And the last one is to find the subarray that has the largest summation that crosses the midpoints. Okay. So let's look at those questions separately. Actually, the hardest one is the one that we'll look at first, which is to cross the midpoints, right? We want to find find the maximum subarray that cross the midpoint. Okay. But as for now, it's already much easier than the original problem. Okay, this is a new problem. This is not a smaller instance of the original problem. Okay, the subarray that cross the midpoints actually consists of two parts, as we showed in the previous slide. The left half is from I to mid, right half from mid plus 1 to I. So how do we find the subarray that has the maximum maximum summation? So it looks like we don't have a better option rather than use for loops to iterate over all possible conditions. Okay, so here's the code for finding the maximum crossing subarray. Okay, which is for so the name of the procedure is like find max crossing subarray, and the meaning is to find the maximum subarray that crosses the midpoints. Okay. All right. So because this problem, this subarray consists of two parts, so we will use two variables to store the summation for the left part and the right part respectively. So they all start with negative infinity values, because that is the value that's smaller than any number, right? And for line 2, we use a temporary variable sum to store the current summation. The first for loop is a loop that iterates over the left positions, all possible positions for the left index I. Okay, it starts from the mid down to the low. Okay, and we'll need to consider the summations at each point, right? When we have when we scan over the left half of the subarray, we add that element to the summation variable. And if that summation is greater than the current left summation, we will mark the maximum price and the maximum summation, right? And mark the corresponding maximum index for I, right? And we do the same thing for the right. We will let the index j starts from mid plus 1 and iterates over all possible positions for j from mid plus 1 to high, right, to the last point. And we will add each element that we scan in each iteration to the summation, to the sum variable. And if it's larger than the right sum, we will mark the maximum value and the corresponding maximum position for j. Okay. And lastly, after the two scans are done, we will return the left index, the right index, and the total summation of the maximum subarray. Okay, so this is a kind of an easier problem than the original problem, because we have a constraint, right? We have a constraint that the midpoint is part of the subarray, right? So we can always start from the midpoint, scan to the left and scan to the right, and mark those starting index and any index that results in the maximum summations. All right, so that will return in, let's skip this slide because I have just gone through it manually on the previous slide. You can keep reading it if you need some time to understand the pseudocode. And also the textbooks provides very detailed explanations. Okay. So here we can also briefly analyze the running time of this find max crossing subarray procedure, because the total number of iterations is actually determined. It's just the length of the original input. So it's actually a linear running time algorithm. Okay, it's no different from running one complete for loop over the entire input sequence. All right. So now we have this procedure at hand, right? It solves the third case of the subproblem, right? We solve the case where the sub-array crosses the midpoints. Okay, so now we can use it to implement the final find maximum sub-array procedure. Oops. Sorry, the order of the animation is problem. Okay, so now we can like define the algorithm, which has the name find maximum sub-array. So it's a recursive algorithm because we now need to solve the first two cases recursively, right? So first of all, if a sub-array contains only one element, that's what the first line of code deal with, right? It will directly return the current indices and the current elements in the array. Okay, so this is the boundary case of the recursion. Otherwise, we need to divide it, right? We need to find the midpoints, right? And we will solve the left half by calling the function itself recursively. So this is the first call of the function itself. It's called on the left half. So the starting index is low and the ending index is mid. It's not high, okay? And it will return the left low index, right high index, and the summation for the left subproblem. And similarly, we need to conquer the right half by calling the function itself on the right half, which is from mid plus 1 to high, right? And the third case is something we just written in the previous slide, right? We need to call the procedure that solves the sub-array that crosses the midpoints, right? We just directly call them find max crossing sub-array with low as starting index, high as end index, and the midpoint in the middle. Okay, so these three conquering steps are done, and we have collected the results right into those variables. The next combined step is to compare which one has the larger array. Okay, has a larger summation. So if the left part has a larger summation, we will return the index, the indices, and the summation from the left. If the right has a larger one, we return the right. If the cross has the largest summation, we return the cross indices and the cross summation. And we're done with the algorithm. Okay. So that's a complete code. And let's see if we can find it easier to get if we go through some examples. Okay. So let's just use the case for the stock price, right? We have the input array, the net change as an input array, okay? And our A is this array. So let's directly call the algorithm on these inputs. So as the algorithm defines, we need to compute the midpoint, which is 8, right? And there will be a first recursive call on the left half from 1 to 8, and the second recursive call from 9 to 16. And the third call is the crossing sub-array call that's given this midpoints, given this index A at midpoints. Okay. So now on this page, let's focus on the third part, third case. This is something we can quickly find. So the midpoint is 8, right? This max crossing subarray basically scans from the mid to right, right? And scan from mid to left, and scan from the mid to right, right? So basically, it finds that the maximum subarray in this case is this segment from elements 18, 20, -7, and 12, right? We can find that easily. Find that if we go further right, we will encounter a lot of negative numbers. So that will not bring any more profits. And if we further go left, it's also a lot of negative numbers. Okay, so the result is a correct one here. So the cross summation is for 43. We can memorize this value for now. All right. So remember that is just one step, and we need to step into this first recursive call, right? Remember there's a first recursive call. So if we step into this recursive call, it will look like this. It will look like we're constraining our elements arrays into this first sub array, right? And this within this recursive call, we still need to compute the midpoints, right? And in this midpoint, it is the index 4, right? And this incurs further recursive calls, which is from 1 to 4 and from 5 to 8 respectively. And there is a further cross max crossing subarray call, right? So this one is also something we can manually examine, right? If we start from the midpoint 4 here, scan to the left, we see very big negative numbers, so we'll probably stop, right? And towards the right, we also see a lot of negative numbers. So it looks like in this case, the crossing subarray is the one that has 2 elements, right? Which returns a cross summation as 17. Okay. So we can, there's no time for us to, no space to limits to either to like list all recursive calls. We will go one step further, right? Which is this one, and we will stop. So let's went into this recursive call deeper, which gives us a new midpoint, right? A new midpoint is 2. So 2 new midpoint, 2 new subarrays recursive calls occurs, and 1 new crossing subarray call is encountered. So this crossing counts actually gives us a cross summation, which is 5. As you can see, it's getting smaller, right? Getting smaller. And this one is something we can examine visually because there's only 2 elements in it. Okay, so the maximum subarray of these 2 elements is actually 13 alone, right? And the maximum subarray for this one is 20 alone, right? So at this level of A14 on this recursive call, we need to compare the 13, 20, and 5. And obviously the 20 has the largest summation, so the maximum subarray for elements ranges from 1 to 4 is the 20. Okay, and these results will be returned to the upper level, okay, which computes the maximum subarray ranges from 5 to 8, and also the one that crosses the midpoints 4. Okay, and we will find that the results is what we already know, shown in the earlier slides. Okay, so lastly, let's analyze the running time for the find maximum subarray. Okay, and for simplification reason, we will assume the length is always the power of 2, so that we can ignore those ceilings. We can always divide those numbers. Right, let's use T of n to denote the total running time, right? Let's consider all those code, right? So the division, it takes constant running of time. And also in the base case, right? If it's a base case, it takes constant running time. So T of n equals a constant. So when we have larger inputs, the division takes constant amount of time. The first recursive call from line 4 to 5, it is a subproblem with half the elements size as inputs. So the total running time can be indicated by T of n over 2, right? And from line 6 to 7, it is the recursive call on the second half, which is also a smaller a subproblem, which takes T of n over 2 time as well. And we already know that the line 8 to 9, the find max crossing subarray, it takes linear running time. And the input size is n, so the total running time is big theta of n. And for the combining parts, it's just if else, right? So these are constant time operations. So in total, the combining step takes big theta of 1. Taking all these parts together, we will have the total running time is the constant plus 2 times T of n over 2 plus theta of n, right? And all these simplifies to T times 2 times T of n over 2 plus theta of n. So this is the equation, the recurrence equation that we have for the maximum subarray problem, right? Can complete the recurrence further, right? It looks like this. I think you may have already noticed, right? It is actually the same form as merge sort, okay? Which means we can directly apply our knowledge about merge sort. The total running time for this maximum subarray algorithm, it runs at the growth rate of n times logarithm of n, right? Which is a better efficiency than the brute force solutions. If you want to brute force this problem, it takes n squared. All right, so in our next lectures, we will introduce first the substitution method. So I would recommend you to read it ahead of time from pages 83 to 86. And on next Tuesday, we will introduce substitution and the recursion tree method. I think we can also touch a little bit about the master method. And for master method or master theorem, we will have a more complete example and more other examples on the Thursdays, on next Thursday's class. All right, so that's the example, that's the lecture for today. I strongly recommend you to go through the code, and I will release the homework later this evening. It's ask you to implement the find maximum subarray. Because you already have the pseudocode, I think it's straightforward to complete it in Python. But also I have another variant of it, which is a slightly different problem, but which can be solved with the similar divide and conquer thoughts. All right. If you have any questions, let me know now or send me emails.
I have a question.
Yes.
For the homework assignment number 1, could we use, or the programming assignment, could we use VS Code instead of Jupyter Notebook?
Yes, you can.
Okay, perfect. Thank you.
Yeah.
Thank you.
All right. Thank you.
Next meeting is in person, right?
Yeah, next meeting will be in person.
Sounds good. Thank you.
Thank you. For Vim mode, I don't know that. In Jupyter, if you open up a Jupyter Notebook in browser, I don't think there's a Vim mode, but in VS Code, there's a Vim mode.